So here I'm back. Hi. All right. So the gain of this transistor, it says 20 to 70. Now, that's not 20 to 70 amps or ohms or volts or anything else. It's like a gain factor. In other words, it will amplify whatever you put in, it amplifies it, let's say 20 or 70 times. Now, the reason it says 20 to 70 is that it's impossible for each transistor to be exactly the same. In other words, one transistor comes off the assembly line, it has a gain of 35. The next one has a gain of 55. The next one has a gain of 23.5, and so on. Wake up, Jeff. Sorry, we'll take a break in a second. Boy, I must not be too energetic this morning. Say, okay, so well, they come off the assembly line. Man, they could have any kind of gain. You don't even know. Anyway, so they give you a range. This gain will have a gain. This transistor will have a gain of somewhere between 20 and 70. Well, here's the deal. When you substitute transistors, you can stay the same or go up in voltage. You can stay the same or go up in current, just like diodes, but you kind of have to match the gain as close as you can. But it doesn't really have to be all that close. We have generally about 3 categories of gains: low, medium, and high gain transistors. Low gain transistors have a gain of up to about 250 or so. This is somewhat arbitrary. 250 to 750 maybe is a medium. 750 and above would be a high gain transistor. Almost any low gain transistor will substitute for almost any other low gain transistor. Highs for highs, mediums for mediums, and so on, as long as the voltage and current is the same. So let's take a look at some of these transistors. Let's say that we have a bad 2N3055, 60 volt, 15 amp, low gain, right? We got a bad one, and we need to get a substitute. Look in your chart here on page R-7. Right underneath the 2N3055, find this 2N5881. Could I use that as a substitute?
Yes.
Absolutely. Look, the I sub C, the collector current 15 amps, voltage 60 volts. That's exactly the same. The current gain, the H sub FE, the beta, 20 to 100. Definitely, it's almost exactly the same transistor. How about the one right above it? How about that 2N6576?
No.
Why not?
2K to 20K.
Look at the gain. Sure, the gain says 2K to 20K. That's 2,000 to 20,000. I'd say that is definitely a high gain transistor. There's no question about that. Yeah, Claude.
2,000 to 20,000 what?
A gain factor. It has a gain of 2,000. It has a gain of 15,000, whatever.
Right, so that's what they... That's the unit they call it.
Yeah, I guess so. You know, I don't know. They just say it has a gain of 50. You know, that's all. It's not really a unit. I guess that's the Elvis that we're looking for.
Oh, yeah.
It's a gain of, the gain is 20 to 70 Elvis. All right. So I don't know. Anyway. All right, let's look at a few more. How about under 15 amps, 80 volts, 2N5880? Could I use that one? Why not?
Yeah, you can. Why not?
Could I? 5880?
Yeah.
It's PNP. What does that mean, Hondo? I can't use it, right?
Reverse polarity.
Right, the polarity would be reversed, right. Okay, so I can't use that one, but we can get pretty nuts here. Let's go down 15 amps, 350 volts. 2N6251, no problem. It's a low gain transistor, and it says 6 to 50, but that's still in the ballpark. That would work. It would be very expensive, but it would work. Let's go really nuts. 20 amps, 450 volts. MJ13334, no problem. See, it's higher current, way higher voltage. The gain is 10 to 60. Okay? So that will work too. And so that's really all you have to look at. Now, to make your job easier, I've got these things. Substituting transistors. Very often you cannot find the exact right transistor. Now, we'll be going over some suggested parts that you should get. And in the back of your blue book on page, you don't have to turn there, but on page 82 or 83, there's a list of recommended parts that I suggest that you get. But a lot of times you'll need to get a transistor and you won't have the exact right part. I mean, we do use dozens and dozens of different kinds of transistors. And so you have this thing. Now, what ECG is a company that manufactures a line of universal replacement components. Not just transistors, but diodes and integrated circuits and everything. Good move, Jeff. Thank you. Thank you very little. All right. So here's what this is. In the back of the book is a list of all transistors and integrated circuits and diodes known to human science back here, just about. I mean, there's just a shitload of them back here. And it's in alphanumeric order. Let's say that we have a 2N3055 and it's bad. Let's look up 2N3055 in the back. And it's in alphanumeric order, and it would be on page 2-28. And it's kind of in the second column over, the fifth paragraph up, 2N3055. Everybody find that, 2-28. 2-28. Like right around there somewhere. And it says that a 2N3055 is the same as an ECG what?
130.
ECG 130. Then all you have to do is pick up the phone and say, hey man, I need an ECG 130. And the guy will say, hey, come on down and get it. This makes your job a whole lot easier because we do use lots of strange transistors. Well, not lots of them. We use some weird transistors in our industry. And you may not be able to get the exact replacement. But most towns, I guess except Yuba City, have some kind of an ECG distributor. I mean, certainly there's a TV repair guy in every town. Where does he get his parts? A lot of them get them from the local ECG guy. Now, there's another really cool way to use this book. Let's say that you have a transistor laying around in the shop and you want to know what the specifications are. You want to know if you can use it as a substitute for something else. Let's say you have a 2N3055 laying around and you don't know what the hell the specifications are, which you wouldn't. And the schematic doesn't tell you either. The schematic doesn't tell you specifications, it only tells you part numbers. So you look it up, you find that it's an ECG 130. Then in the very front of the book is the product index. And let's look up the ECG 130, and it would be on page 1-9. Now this is just the index. This is telling you where to find the information. So if you look on page 1-9, left-hand column right in the middle, ECG 130, and it says to turn to page 1-40 to find the info. So let's turn to page 1-40 now. It takes a little while to get used to how this book works, but once you do, it's a real important book.
Where did you find?
In the index in the front,
Yeah.
ECG 130 on page 1-9.
ECG 130. Where's 130?
Oh no, page 1-9.
Oh, okay.
See, ECG 130.
Gotcha.
Okay, page number 1-40.
Gotcha.
All right, so turn to page 1-40 now. And let's look up the ECG 130. And here it is right in the middle of the page, and it says ECG 130. What does it say about it? Well, it says it's an NPN transistor. It says it's made out of silicon, which it is. There's another type of material called germanium that we don't really use anymore. It says that it's commonly used as an audio frequency power amplifier, which it is. It may not be used like that in our case, but that's what it's commonly used for. It's complementary to an ECG 219. That means it's the same specs but opposite polarity. Now, let's see what the specifications are. Remember, we've got some different voltage ratings, but the only one we're interested in is the second column over, collector to emitter volts. Remember that? V sub CEO. Or as it says here, BV, breakdown voltage. Okay, what does it say about the voltage?
60.
We know that's true. We just looked that up. I shouldn't have erased it, but it was up here, 60 volts. So that's cool. Maximum collector current, I sub C.
15.
That's true. That was the original specs. Now, look over here, current gain, H sub FE. What's it say?
40.
See, it says 40 typical, right? Well, what was the original gain? 20 to 70, right? 40 is right in the middle, so it's an average. So what they've done here is using the exact same criteria that I just outlined in my previous utterance before the break. That is the thing that the substitution method that we just went over. They're doing the exact same thing here, aren't they? So this makes your job real easy. This and your blue book are two very important things to have. Another kind of transistor that we do use in games, and it's the one that I've given you, and it's called a Darlington transistor. It's called a Darlington transistor. Now, there's nothing really mysterious about a Darlington transistor. A Darlington transistor is simply two transistors in one single package. In the Darlington transistor, the emitter of one transistor is connected to the base of the second transistor. The two collectors are tied together. And all of this is in one single transistor package like the one that I gave you, the TO220 package that I gave you. You still end up with a base lead coming out, and a collector lead, and an emitter lead, and they're still in alphabetical order. That never changes in the TO220 package. Any transistor that's in this package, B, C, E, the center lead is also connected to the metal tab on the top. All that's exactly the same. Now, other than the fact that it takes less space than two separate transistors, what do you suppose the advantage is of two transistors in one single transistor package?
Does that take less current to drive it? Less voltage?
No. It has more of something. Yeah, what do we call that?
Amplification.
Gain, yeah, the gain. Heads up. Whoa. Hey. Did you play women's softball too? Keep your hands down. All right. It's hard. Oh, you said gain? Oh, I'm sorry. Well, then you deserve that. Well, you deserve.
So did I. I said that too.
Oh, Jesus, here you go.
I wanted the Kit Kat.
Kit Kats are gone. God, you big babies.
Give him mine. Give him the kit. Give him the cat.
Yeah, here's your damn Kit Kat. Oh, sorry. You can put it in your crane and make some money off it. That's from Jeff. All right. Yeah, it has more gain. That's the deal. A Darlington transistor, in a Darlington transistor, the gain of the first transistor is amplified or multiplied by the gain of the second one. For instance, let's say this first transistor had a gain, HFE, remember his gain, of 100. The second transistor maybe has a gain of, let's say, only 20. Together, this whole thing has a gain of 2,000 or 2K. Remember that one transistor, I asked you if you could use it as a substitute for the 2N3055, and you said, no way, because the gain was 2K to 20K. Remember that one? That had to have been a Darlington. The only way that we can get gains of 1,000 or more is with a Darlington circuit. Now, really, this guy Darlington, another dead guy, I assume he's dead anyway, I don't really know, I guess he probably is. He actually figured out a way to hook up vacuum tubes in this circuit called a Darlington. When we changed it to transistors, we still call it a Darlington. And where we use the Darlington transistor almost exclusively is in the pinball machines. These are the coil driver transistors in a pinball machine. The part number I gave you is the one that you use, TIP 122. It's like I think it's a 5 amp, 80 volt, maybe 100 volt transistor, something like that. You could look it up in your book, but we won't do it right this second. And where we use this again is in the pinball machine. Whoops, I better not erase this yet. Let me put this back together here. Now, when you test the Darlington, no, I really screwed this up. When you test the Darlington, it's going to check a little different than a regular transistor. And here's what you'll see, and I'll have you do it in just a second here. When you test the Darlington, when you check it from base to collector, you get a perfectly normal reading. You get a junction drop one way and open the other, just like normal. That's fine. But when you check it from base to emitter, the junction drop you get will be somewhat higher than normal. Instead of like 0.9 or something, it might be 1.1 or 1.2 or something. The reason for that is that you have a PN junction here between the base and emitter. And it is in series with that base to emitter junction as well. In other words, when you're going from base to emitter, you're going through one PN junction in series with another, so that you get a normal junction drop here, but something somewhat higher when you reverse the leads. When you move the lead to the emitter. When you reverse the leads, though, that's perfectly normal. Open reading, just like before. One more time. Base to collector, normal junction drop. Base to emitter, something somewhat higher. Reverse the leads, open. Now, final check. Remember, between the collector and emitter, in a normal transistor, what do you see? You see an open both ways, right? Open both ways. Well, in the Darlington, like the one you have there, between collector and emitter, you'll get an open one direction, but when you reverse the leads, you'll get a junction drop. That's pretty interesting. Open one way, junction drop the other. What part do we know that tests like that? Open one way and a junction drop the other. That's a diode, isn't it? Internally, inside this thing, in addition to the two transistors, there's also a diode in here, built into it. This diode is a protection diode. Now, normally, of course, you would never expect this diode to conduct, would you? Because the current is going to go in the direction of the arrow. This thing's facing the wrong way. This protection diode is there to protect the transistor from destruction in case the polarity becomes reversed for some reason. If the polarity gets reversed, it can wipe out the transistor. And that can happen in a pinball machine, and I'll tell you more about it on Saturday. Right now, all I want you to know is that it exists. It's a protection diode, and when you check this transistor from collector to emitter, you'll get a junction drop one way and open the other. One more weird thing on some Darlingtons, and these may be like this. We just really discovered this recently. Some Darlington transistors, for reasons that I don't know, I don't really care, but I don't know either. Some Darlington transistors have a couple of resistors in here as well, connected like this. When you check between base and emitter, you may not find an open reading the other direction. You may find a junction drop, somewhat higher junction drop one way. You may get a reading the other direction of some number of ohms. I'm not sure how many. You're going to try it right now. And the fact of the matter is, the reason I'm not worried about this is, when these transistors fail in a pinball machine, they always dead short collector to emitter. So it's really easy to find bad transistors. I'll talk to you more about that on Saturday. And let's take a look at the SCR, the silicon controlled rectifier.
The schematic symbol for the SCR is pretty much the same as that of a conventional diode. We still have the anode and the cathode, but since this is a controlled rectifier, we have a third element, which is the controlling element. Well, in the transistor, we called the control the base. But in the SCR, it's called the gate. And the gate lead may be seen drawn as coming out the right side of the symbol or coming out the left side. Let's put the SCR in a circuit and see how it operates. As long as the SCR is turned off, no current flows through the SCR at all. However, when the SCR is turned on, current will flow from the positive terminal of the battery through the lamp and through the SCR and back to the battery. When the SCR is turned on, it behaves like a normal diode, and since it's pointing the same direction as the current flow, the lamp will be lit. Let's take a look at the actual demonstration circuit itself. Notice that the gate, which is the middle lead of the SCR, isn't connected to anything. Unlike the transistor, which requires a small amount of voltage on the base in order to turn it on, the SCR is actually operated by a small amount of current. So sensitive is the gate that I can actually turn it on by simply touching my finger between the gate and the anode. Notice that the lamp turns on. And notice too that once the SCR is turned on, it stays on. Notice that the lamp is staying on now, and it stays on until you break the connection, just like that. SCR failures are generally pretty straightforward, and here's a typical type of thing that you'll see when you have a bad SCR. In this case, the lamp is staying on all the time, and even if I break the connection to the power circuit, which normally turns off the SCR, as soon as I reconnect it, the lamp turns right back on again. So this SCR is always on. It has a short between the anode and the cathode. SCR specifications are the same as those of conventional diodes.
Yeah, right.
Voltage and current.
Now, we don't really use SCRs much anymore at all. In fact, I honestly can't think of anything in a current piece of equipment that uses an SCR. Where they were used almost exclusively is in the older Bally pinball machines. There were SCRs for every lamp. All the lamps in the game were activated by SCRs. The cathodes will go to ground. Here, I'll draw a slightly less confusing ground. There we go. And the gate was connected to the computer system. Whenever the computer wanted to energize a lamp on the play field, it would simply send a little bit of juice out to the gate of the SCR. That's called gating it, gating the SCR. And then the SCR would turn on, and it behaves like a diode, and since it's pointing that direction, the electric current would flow from the power supply that powers the lamps this way, through the lamp, through the SCR, and to ground, and it would light the lamp up. Well, troubleshooting these things is pretty easy. There's not a real transistor type test that I can show you on this. Not really. In fact, the only junction drop you get is from gate to cathode. But it isn't necessary. It was never necessary to test the SCR, because if you had a lamp that never lit up, the SCR was bad. If you had a lamp that stayed on all the time, the SCR was bad. That's all there was to it. I mean, that's the only thing that ever failed in the circuit, and that's was so simple that you'd go, oh, that light isn't lit up. You look in the schematic, it said that this was hooked up to SCR number 5, and you change SCR number 5, and it would work. Well, we don't use these anymore, but we use a similar type of device, and there's nothing in your book about this device because, well, to be quite frank about it, I haven't had time to really write about it. But there's another part that you do definitely need to know about. Those of you at NAMCO really need to know about this. You probably already do. There's a part that we use now to control things called a triac. Triac. And the triac is an AC controller. In fact, that's where the ACK in triac comes from. It has 3 terminals, and it works on AC, so they call it a triac. The schematic symbol for the triac looks a lot like the SCR, but it's actually like 2 SCRs hooked up together. In other words, if I draw an SCR here, looks like a diode with the gate. Remember that thing coming out? It's called the gate. And we still had the cathode and the anode. If I extend this out and just draw another arrow pointing the other direction, now I have a triac, basically. Because that's all it is. The SCR would only control current flowing in just one direction, the same direction that the arrow pointed. The triac can go both ways. And here's how the triac works. It's very, very simple. Very simple. In fact, I'm sorry, but I have to redraw this a little lower here. In the triac, instead of having an anode and a cathode and a gate, we have the gate, that's the same. This is called main terminal 1 and main terminal 2, if I'm not mistaken. They're actually interchangeable. And where we use these guys is to power things like, for instance, in a basketball game. You know that there's a bar that locks the balls in place, and that bar raises up when you put the coin in and the balls roll down. Well, the thing that raises the bar is either a motor or a giant honking solenoid. I mean, just a giant coil that goes clunk and energizes and raises the bar. Or it's a motor that spins and raises it up. Regardless of that, these are powered by triacs. If it's a motor, that's the schematic symbol for a motor, just a circle with an M in it. And it's connected just like this. It's really incredibly simple. Here's your AC power plug coming in, your AC power. Presumably there's a fuse in this line somewhere. You don't really have to draw the fuse in. And the gate is connected to the computer system. When the computer wants to raise the bar, or in a skee ball machine, energize the solenoid to let the balls come down, or anything that needs a massive motor or a big coil, instead of using a transistor, we use this triac. When the computer wants to energize the thing, the motor, the solenoid, whatever it is, it simply sends a teeny tiny amount of voltage and current out to the gate. It's very sensitive. The gate's very sensitive. That energizes the triac. It's just a switch. It just closes the triac. In other words, it shorts out right across the triac, completes the circuit. Obviously, we have a complete circuit now, and the thing energizes. When the computer wants the thing to shut off, it simply removes the gate voltage, the triac turns off, it's now an open circuit, the motor obviously stops turning. And that's all there is to it. It's very, very simple. There's just one device, this triac thing, that controls this stuff. And again, there is no test for this thing. The only junction drop you get is like from gate to main terminal 1, I think. I'm not even sure about that because I've never tested one. Same deal. If I have a problem with a basketball game and the bar never raises, the triac's bad. If I have a problem where it's blowing that fuse, and as soon as I put the fuse in, the motor starts to turn, or the solenoid energizes and stays energized all the time, it's the triac. That's all there is to it. In fact, you can even get these things at Radio Shack. I don't even stock triacs because they do have at Radio Shack like a 600 volt, 8 amp triac. And they're rated by voltage and current the same exact way that diodes are. And I turn to page R10 and let's look at Zener diodes. Everybody's always interested in what the hell this is, a Zener diode, because it does have such a strange name, in this case named after Clyde Zener. No, not really. I don't know who it's named after, actually.
Bruce.
Bruce Zener? Okay. Anyway, a Zener diode looks, schematic-wise, looks like a regular diode, like this, and it has a cathode, and it has an anode, just like before. But to show you that it's a Zener, it has these little angular bits that kind of form like a stylized Z for Zener. Zener diode. Now, if you look at the chart, look down the far left-hand column here, the far left-hand column, where it says nominal Zener voltage. And if you look at these voltages, they're nothing like the kind of voltages that we've seen so far. I mean, so far, when we've been looking at voltages for diodes, for instance, we had 50-volt diodes, and 100-volt diodes, and 400-volt diodes. And when you look at these voltages, they're real strange. They're like 6.8 and 8.2, 9.1, 10, 11, 12, 14. The Zener diode voltage means something completely different than the voltage rating of a regular diode. In fact, the Zener diode works in a completely different way. In fact, the only reason it's called a diode is that it has two leads. Diode, two leads. Other than that, it actually works completely different. It's a whole different animal. Here's the deal. Every Zener diode has its own voltage rating. Let's say, for instance, that we have a 12-volt Zener diode. Here's what this means. As long as the voltage on the cathode is less than 12 volts, or I guess I probably should say 12 volts or less, the Zener does block just like a regular diode does. Now actually the Zener diode would always conduct in that direction, the same way the arrow points, but we never use it that way. Current is never allowed to go through the Zener diode in the forward direction because it wouldn't do anything. It just doesn't do anything. As long as the voltage on the cathode is 12 volts or less, the Zener does not conduct. It blocks it just like a regular diode does. But if I exceed the Zener voltage, the Zener diode will start to conduct. And this is the only part that conducts opposite the direction that the arrow points. It's like I before E except after C. It's the exception to the rule. Tough bananas, that's the way it is. It's the only part that does this. And here's what it does. I've got 2 volts on the cathode, does not conduct. 3, 4, 5, doesn't conduct. 8, 9, 10, doesn't conduct, blocks it, 12. If I exceed the Zener voltage, let's say I put 13 volts here on the cathode, the Zener diode does start to conduct. But it doesn't just snap on. It doesn't turn on instantly. The Zener diode's a real selfish little bastard. If you can give human attributes to a component, this is the most selfish little bastard you'd ever want to meet, because here's what it does. It says, okay, you put 13 volts on my cathode, I'll start to conduct, but I'm going to keep the first 12 volts for myself. I'm a 12-volt Zener diode, damn it, I want the first 12 volts. Anything that's left, you can have out my anode over here, and it'll put 1 volt out over there, out the anode. In other words, it says, look, I'm a 12-volt Zener. I want to keep the voltage across myself at 12 volts at all times. Zener diodes are sometimes also known as regulator diodes, because that's how we use them. The Zener diode will try to keep a fixed voltage across itself at all times. Anything that's left over, it'll put out the other side. So for instance, if I have the same 12-volt Zener, and I put, let's make the math easy, I put 22 volts on the cathode, keep the first 12 for itself, I'll get 10 volts out the other side. Now there's a couple of different places where we might want to use a Zener diode like this. For instance, we might have a circuit that has a 100-volt power supply in it. Let's say there's some circuit that needs 100 volts, and there's a 100-volt power supply. But there's another circuit in the same unit, whatever it is, that needs only 20 volts to operate. Instead of making a separate 20-volt power supply, they might use an 80-volt Zener diode, run that 100 volts through it, and what would come out the other end is 20 volts. And then that would go to the other circuit that uses 20 volts. In other words, it would cut down a known amount of voltage. That's one way we can use it. That's not the most common way, though. The most common way to use a Zener diode is like this. They will ground the anode of the Zener diode. Let's say it's a 12-volt Zener diode. The voltage right here will be kept at exactly 12 volts no matter what. In other words, there's some kind of a power source coming in here. And I'm intentionally being kind of nebulous about this because it doesn't matter, where this comes from to explain what this part does. Let's say we've got this power source. Let's use an automobile as an example. Most cars have like a voltage regulator circuit in them. The deal is when your car is at idle, let's say, the alternator or generator in your car is putting out 12 volts, perfectly normal. But when you start stepping on the gas, you start going faster, the faster you go, the voltage would start to rise. We don't want the voltage to be 18 volts going into your 12-volt battery, so they have a voltage regulator circuit that regulates it. This does essentially the same thing. As long as the voltage here is less than 12 volts, this doesn't conduct. But if this starts to go up above 12 volts, the Zener does start to conduct and drags any extra voltage to ground, basically. There will be a resistor in here that I haven't discussed with you. The voltage, the extra voltage will be dropped across that resistor. The voltage right here will stay at exactly 12 volts no matter what. We use these as voltage references. And I'll point it out to you later on in a couple of other circuits where we use the Zener diode as a voltage reference to keep the voltage there at exactly a certain point. Here's a cool way to think of the Zener diode. Imagine a water tank. I have a pen full of water here. There's water. And let's say here's a hole in the water tank, a spigot with a pressure gauge. There's the pressure gauge. Obviously, the more water I have in the tank, the higher that pressure will be, correct? As the water goes up, there's going to be more and more pressure. I've got a hole here in the side of the tank. I add more water to it, the pressure goes up. Add more water to it, pressure goes up. At this point, if I add any more water to it, I can't get the pressure to go up any higher, can I? Because if I add extra water to it, it's just going to flow out the hole and land on the ground, right? The pressure is fixed. Same thing here. I've got a hole here, 12 volts. Put in 1 volt, 2 volt, 3 volts, 4 volts, 5 volts. It continues to build up the pressure. When I get to 12 volts, if I try to put any more voltage on this thing, the extra current, the extra voltage is going to go through the Zener diode to ground. It's going to come out and land on the ground. Same thing. Yeah?
So is that safety feature unlimited voltage? Good for unlimited voltage, or is it?
It would be, yes, it would be, depending on the size of this resistor. There's always a resistor here, and I'm getting more advanced, and I don't want to, called a voltage dropping resistor. The extra voltage is actually dropped across this resistor, and it gets hot as shit. It gets really, really hot. Don't worry about it. The reason why I'm telling you not to worry about it, and I'm not copping out here, is that for the most part, Zener diodes will test just like regular diodes. When you have it looks like a regular diode too. You don't have one in front of you. It looks like a regular diode. There's nothing unusual about the way it looks. When you have a Zener diode failure, it will check, when you have a good Zener, it will check like a normal diode, open one way and a junction drop the other. When it fails, it will probably short circuit just like a regular diode does. However, there's a however for you. Occasionally, Zener diodes do a really weird thing. Occasionally, when a Zener diode fails, it will lower its Zener voltage, or it'll change its Zener voltage, and it usually lowers it. Turn in your blue book to page, gosh, I think it's 17 or 18. Let me see. No, I'm full of it. Wait a minute. I'll tell you. Page 32. Oh, I was really close. Page 32. On page 32, this is the Williams high voltage power supply. This is the power supply that powers the score displays in a Williams pinball. The score displays in a pinball are not LEDs. A lot of people think they are, but they're not. They're neon gas discharge display tubes. They take high voltage. They take 200 volts to operate. To get that 200 volts, they actually make two different power supplies. One is plus 100 volts, the other one is minus 100 volts. The difference, of course, between plus 100 and minus 100 is 200 volts, and that's where it gets its 200 volts. Well, what we have here are a pair of voltage regulator circuits, and we're going to look at these in great detail this afternoon. But what I want you to see is this. Look at the schematic diagram. Find this transistor Q1, right up here on the top, Q1. Notice the output voltage, 102.4 volts. Notice the base voltage, 103 volts. Remember, the base is 0.7 different than the emitter. Remember that? Okay, in this case, 0.6. Remember, 0.7 is an average reading, so in this case, it's really 0.6. This Zener diode is a 100-volt Zener diode. It's a 100-volt Zener diode, and the tolerance is plus or minus 10%. really. So it could be anything up to 110 volts. And here it's actually pegging this at 103 volts. This Zener diode is responsible for keeping the base voltage at exactly 103 volts so that the output stays at exactly 102.4 volts. In other words, this is a regulator diode. This diode is keeping the base voltage absolutely constant so that no matter what happens here on the input voltage, as it can rise up depending on what your AC power is doing, the output voltage stays perfectly constant because the base is kept at a constant voltage by that Zener diode. Well, here's the deal. The Zener diode can mysteriously change its Zener voltage sometimes, and what it does is it drops. I've never seen it go up. It's always dropped. Here's what happens. You get to the game, in this particular case, and the score displays are not working at all. The game coins up, plays, makes all the game sounds, but just no scores. You measure the power supply voltage. We'll do this on Saturday, and you find, let's say, the minus 100 is perfect. The plus 100 is only 40 volts. Oh, well, that explains why the scores aren't working. You need 100 volts. It's only 40. And this is what happened to me. So I say, well, I've got a regulator problem. It's got to be one of those transistors or Zener diodes in there, and I check them all with the power off, as you should do. They all check perfectly okay. Next step, turn the voltage on, turn the power on, and carefully check the voltage across the Zener diode. Put 1 meter lead on one side of the Zener, the other on the other side, measure the voltage across it. If it's a 100 volt Zener, it should have 100 volts across it. In this case, it only had 40 volts across it. The Zener was bad. I changed it, and that's all there was to it. I suggest that you read through this article tonight. I demand that you read through this article tonight. Anyway, but the point I'm making here is this, that in a Zener diode, most of first of all, they're not a real common failure except for this circuit. It is very common failure in this circuit. When you think you have a Zener diode failure, check it with the power off first. If it appears to check good, you will have to turn the power on, simply measure the voltage across it. Whatever the rating of the Zener is supposed to be, that's how much voltage you should read across it. The Zener diode, if the voltage rating is not listed on the schematic, it is sometimes, but it's not always, you get the part number off the Zener, like 1N4764, or whatever this part number is. Well, I don't know. And you would look it up in your ECG book. Your ECG book tells you how many volts the Zener is supposed to be. Big advantage, because without the ECG book, you might not be able to figure out what the voltage is supposed to be. So Zener diodes. Now, when you substitute a Zener diode, obviously you cannot change the Zener voltage. I mean, when you look at those voltages, they're very specific, aren't they? You know, 9.1, 8.2, 6.8 is a very common one. You cannot go up in voltage in a Zener diode. You have to keep that exactly the same. But there are two specifications for Zener diodes. If you look back on page R, whatever we were on there, for Zener diodes. R10, correcto. Zener diodes do have two specifications. One is the voltage rating. You can't change that. That's got to be the same. But the other specification is the same as it is for resistors. You see along the top line, the dissipation in watts, also known as the wattage. People just say it's the wattage. And you can go up in wattage. In fact, I really recommend it. If you have a bad Zener diode in something, and it is a half-watt Zener, which would be listed probably as a 500 milliwatt, 500 thousandths of a watt. A milliwatt is a thousandth of a watt. 500 milliwatts would be a half a watt, wouldn't it? So a 500 milliwatt or 1/2 watt Zener diode, if you find one and it's bad, I suggest you go up to a 1 watt, and maybe that would keep you from having a repeat failure. This thing is called an optical coupler. An optical coupler. And in the optical coupler, on one side is this light-emitting diode. And there's the light-emitting diode. The little arrows come out. The little arrows that come out mean that there's light being emitted from the part. You may see on these optical couplers an E on it for emitter, because that's the thing that's emitting the light. On the other side is the phototransistor. And there's 4 wires that come out of this thing, 2 for the emitter and 2 for the detector. So you'll see a little E on one side and a little D on the other sometimes. Or you may actually see a drawing of the part itself. You know, a little schematic symbol. I don't know, I have got another couple of them around here. Anyway, this is a photo transistor. And it works with light shined on it, when light is shined on it. Instead of putting voltage on the base, you just shine a light on it. It's just like an electric eye. You walk in a liquor store or something, you break the beam, the bell goes off, same kind of thing. And we use these a lot in games. For instance, we use them in the steering wheels, which is what the things are that I passed out. In a steering wheel, as you saw with the trackball, there's a light hub that alternately breaks and passes the light. And that tells the game which direction you're turning the wheel and how fast you're turning it. Some games use optical couplers for accelerator pedals, for gear shifts. We use them all over the place. They're trackball assemblies and so on. The problem with optical couplers is that the entire time the game is turned on, regardless of whether it's being played or not, the LED is on. And the LED eventually burns out. That's what fails in optical couplers. The light-emitting diode actually fails. Also, unfortunately, these LEDs are infrared. You cannot see infrared light. It's the same as with remote controls. If you have a remote control, the LED that's in the remote control is infrared. You can't see that. I'm pressing the button. You can't see the light. But check this out. The camera is sensitive to infrared light. Watch this. See the infrared light blinking on the LED? So you can't see it now, right? But the camera can see it, which is pretty cool. Wow! In fact, what's really cool is if I can actually get this so close, you can really see the little. You can usually see the little. See the little chip of silicon inside? See that little square thing?
Can you explain why?
Beam me up, yeah. Can I explain why what?
How come the camera can pick that up?
With the charge-coupled device, the CCD in the camera is sensitive. Oh, that's a nice shot. Is sensitive to infrared light where our eyeballs are not. Yeah, different codes. It flashes different codes, not different frequencies, but different digital codes. Anyway, oops, I don't want to do that. Where was I? Okay, anyway, the problem is that you cannot see that if that LED is on or off, and that's kind of a hassle. There's a new gadget that is really useful. I carry one in my wallet all the time. I hope it's still in here. It's available from Radio Shack. It's one of the coolest things from Radio Shack. And it's an infrared sensor. Here's the actual gizmo. Oops. It's called an infrared sensor. There's the part number 2760099. It's about $6. This little thing in the corner is sensitive to infrared light. And I can probably demonstrate that for you, although I probably should have tried it out ahead of time. Let's see if this works. You see that? The glow there, right? Now, in this case, it's not just that the camera can see it. Your eyeballs can see it too. If you just kind of, I mean, all you got to do is just hold it up against it, and you can see the glow. You probably can't see it from where you're sitting, but I can clearly see it here. Okay, so this is a really cool deal, and the reason that this little thing is cool, I'm going to pass that around, is that we also use these, for instance, in pinball machines, in the Williams pinball machines, to tell if a drop target's down. When the drop target's down, it puts a little piece of plastic in between there and blocks the beam. Well, when these things fail, the drop targets don't work anymore. And like I said, when they fail, what usually happens is the LED simply burns out. So all you have to do is take your little sensor card, hold it in there. If you see that it's glowing red, the optical coupler is really okay. If you see that it's not glowing red, the optical coupler is bad, or the connections to it are bad, or something like that. So that's really handy. It's really nice to be able to have the ability to check that infrared. Yeah, Ken?
In a situation where, even though I have one of those cards, there's times when I cannot see the light from that thing. It's bright day or
yeah.
the sun or something.
Yeah.
Can that be tested with a meter somewhere?
That's a really good question. Yes and no. It depends on the circuit. Certainly, if you put your meter lead on this pin right here, the collector pin, and you alternately break and make the light beam, and you see that the voltage changes, that would tell you it's doing something. But the amount of voltage that's there depends on the game, and sometimes it's only a fraction of a volt, sometimes it's 5 volts, and I can't tell you what it's supposed to be. Certainly if you had more than one of these units in a game and you could compare the two, that would be something that you could do. But there's not a good test where you could have the optical coupler on your bench, for instance, and just check it with a meter and see if it's good or bad.
You can't test that diode with a meter.
Not really. You get a junction drop of about 1.2 one way and open the other. But I've had them pass the junction test but not emit worth beans. So to be honest with you, what we do is substitution. In a trackball assembly, it's easy, because in a trackball you have 2 optical couplers. One is for up and down, one's for left and right. If it's not moving left and right but is moving up and down, and you swap the two and the problem moves to the other direction, then obviously the optical coupler is bad. On the other hand, when you have problems where there's just one optical coupler, like a steering unit like a steering wheel or something like that, if it doesn't steer, quite honestly, I change the optical coupler and that usually fixes it. Of course, don't forget to clean it first. A lot of times it's just dust and dirt.